Welcome back everyone. In this lesson we are going to learn about the integration procedure whenever we have unequal segments of data points. Okay, so in the last few lessons we have seen that the data points that we are given, they are of equal they were equally distributed. So but in most of the cases whenever you go for experimental experiments, so you will see that most of the data points that you collect, they will be of unequal distribution, and in those cases we cannot apply the direct formulas that we just got in the previous few lessons. So although we can easily apply those methods, the trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, but those methods should be applied now for each segments separately. Okay, so we will see the details in the next few slides. So experimentally, most of the distributed data will be unequal. Okay, they will be of unequal distribution. So what you can do, you can easily apply the trapezoidal rule or Simpson's 1/3 rule or Simpson's 3/8 rule separately in each of those segments. So as a result, wherever in the previous cases these h terms were the same, the width of the each segment were same in the last few slides, but now this h term, the width of the segments, will be different for different segments. That's why we have denoted this h1, h2, hn. So we can easily calculate the area of each segment separately and then sum over the areas to calculate the total area or the integration. Okay, so we have applied the trapezoidal rule here, but you can also apply 1/3 rule or 3/8 rule in the same manner at each of these segments. Okay, so that's one procedure actually, and that's what we are going to follow in this lesson. So you can also actually combine all of those methods like the 1/3 rule, 3/8 rule, or trapezoidal rule. So one common approach is that whenever we have equally distributed data among the overall data set, in the overall data set we might have some of the segments which are of equal widths. Okay, so in those segments we can apply the Simpson's rule. Okay, so that's the one common approach we can easily apply, and in the unequal distributed data points we can apply the trapezoidal rule. So at the equal distributed data points we apply the 1/3 rule or 3/8 rule, and in the unequal distributed data points we apply the trapezoidal rule. So let's look at an example. Say we have an unequally distributed data points. Here we see the x is 0, 0.12, 0.22, 0.32, 0.36. So these are all unequally distributed. Okay, but look at this. Some of the segments have equal widths. Where look at this. The second segment with a width of 0.1. and the third segment has a width of 0.1. So we can apply the Simpson's rule in these segments because they are of equal widths. But wherever we have unequal distributed data points, that means unequal widths, we can apply the trapezoidal rule. So let's look at the details. So what we can do, first of all we will just apply the simple trapezoidal rule at each of these segments. Okay, then we will combine the results of Simpson's rules and trapezoidal rules and compare the results. So first of all we just apply the trapezoidal rule at each of these segments. So in the first segment we have width h1, in the second segment we have width h2, in the last segment we have width hn. So we can apply the trapezoidal rule separately. In the first segment h1 is 0.12, in the second segment we have h2 which is 0.1 actually, but in the first segment, look at this, these function values are actually the function values of this first segment. Okay, these are the function values that are being used to calculate the trapezoidal area. So in this, let's go on to the second segment. We have h2 which is 0.10, that means that is calculated with this width, and we have the function values like this. Okay, so we can similarly go on to the last segment and find the function values and the width, and we can find out the area of the trapezoidal as well. So finally we just got the trapezoidal formula for each of the segments, and we just sum over all of the segments and get the result. So the result is 1.5944801, and it goes to the error for 2.8%. so that is the error whenever we use just the trapezoidal rule for each of the segment. Now let's say we have we have some of the data segments that are of equal width, so we are going to use the Simpson's rule for these segments. Okay, so this is the data table. We have already shown this table. So in the first segment we just apply the trapezoidal rule. So what will happen if we apply the trapezoidal rule? The first segment will have an area of this 0.090583, and in this, let's see the next two segments. That means this one 0.12 and 0.22, this segment has a width of 0.1. Similarly, the next segment 0.22 and 0.32, this segment has a width of 0.1. So these two segments are of equal width, so we can easily apply the Simpson's 1/3 rule. So if we just apply the Simpson's 1/3 rule in these two segments, we will get I2 equal to 0.2758029 and something like this. So in the next three segments, let's see the next three segments 0.32 to 0.36, this has a width of 0.04, and the next segment also has a width of 0.04, and the next segment also has a width of 0.04. So we have in total three segments with width of 0.04. so we can apply the Simpson's 1/3 or 3/8 rule, whatever you like. Let's say we use the Simpson's 3/8 rule at these three segments. So if we just apply the 3/8 rule for these three segments and sum over the areas of each of this segment, we will get an area of I3, which is 0.2726863. So that's the area of those three segments. Next, the next segment has a width of 0.1, and also the following segment has a width of 0.1. So we can apply the Simpson's rule as well again, and if we apply the 1/3 rule now, we can have an area of I4, which is 0.6684701. Okay, in the last two segments 0.64 to 0.7 and 0.7 to 0.8, the last two segments are not equal. So we are not going to use the Simpson's rule, rather we are going to use the trapezoidal rule here because they are of unequal width. As a result, we will get two more integration variables for last two segments, which is I5 equal to something like this and I6 equal to 0.12975. So we have just got all the results from all of the segments. We have just got some results with Simpson's 1/3 rule and some with Simpson's 3/8 rule wherever we have equally distributed data points, and wherever we do not have equally distributed data points, we just use the trapezoidal rule. As a result, we just sum over all of these individual areas and get a result of 1.603641, but with this result we have an error of 2.2%. So if you remember a few slides before, whenever we had used only the trapezoidal rule, we had an error of 2.8%, but now with the combinations of Simpson's rule and trapezoidal rule, we have an error of only 2.2%. So the combination is giving you a better result, a better approximation of the true integration value. So that's the error for combinational result. So in this lesson, we have learned about how we can approach the unequally distributed data. We can apply a single rule, or we can apply a combination of all of the closed methods. That means the Newton course formulas. So that was the basics of approaching the unequally distributed data. Okay, so you can apply the MATLAB course, although I am not attaching the MATLAB code for these distributed data points. You can, because these courses are very much similar to the course that I have given you for the trapezoidal rule or Simpson's 1/3 rule or 3/8 rule. You can just apply those codes for these unequally distributed data points. Okay, so in the next lesson we will learn about multiple integration, that means double integration or triple integration. So these multiple integration are very much useful whenever you are using quantum mechanics or the electrodynamics problems or electromagnetics problem or fluid dynamics problems. So in those in engineering applications, multiple integration frequently occur. So we will look at these, look at the solving techniques for this multiple integration in the next lesson. So till then, thank you so much.